All right, so this week, my goal is to take a look at section 6.2 and 6.3. We'll definitely finish 6.2. I'm not sure how much of 6.3 we're going to get to. I broke it down into 3 different lessons, and we'll just kind of see what we have time for, and we'll just adjust the test if we need to, if we don't get to the 3rd part, but not a big deal. We'll figure it out. All right, so 6.2 is on what we call unit circle trigonometry. And the whole idea behind unit circle trig is the following. So what we have here is a unit circle. Remember, a unit circle is just a circle with a radius of 1. What we can do is we can take and put a point anywhere we want along the edge of the circle. We can put a point like right there. Well, that point has a certain coordinate associated with it. This would be the origin, okay, right there, that would be 0, 0. And to get to that point, there's a certain amount that you could go left, and then there's a certain amount that you could go up. The goal of unit circle trig is to find that coordinate. And what does that coordinate really represent? It really represents an angle. And the way it represents an angle is if you put your initial side like that, and then your terminal side like that, going right through that point, you just created an angle right there. You can move this terminal side wherever you want. Right? And wherever the terminal side hits the edge of the circle, you put a dot where it hits, and the goal is to find the coordinates of that dot. That's really what unit circle trig is all about, finding a coordinate. And then once we have the coordinate of that location, we do something with the x and the y values. So what I want to do is look at this diagram, but I don't want to do it for this angle. That would be kind of arbitrary. I want to do it for four special angles: 0, 90, 180, 270, and see if we can write the coordinates of those. All right, so this is 0. This is 90. Over here is 180. And down here would be 270. Now remember, this is a unit circle. So from the origin to the edge of the circle, it's only one unit in every direction. When in this case, for these 4, either one unit right, up, left, or down. So let's start with 0 degrees. So this would represent your initial side, always right there, and the terminal side, right on top of it. What would be the coordinate right there if you've gone right 1 from the origin? Yeah.
1, 0.
Yeah, this would be the coordinate 1, 0. And that is always the coordinate for 0 degrees on a unit circle. It has an x value of 1 and a y value of 0. Now, let's say we keep the initial side right where it is, and let's rotate the terminal side up to 90. Now it would hit the edge of the circle right there. What would be the coordinate where the terminal side hits the circle? Yep.
0.
That's the coordinate 0, 1. And that is always the coordinate for 90 degrees on a unit circle. Never changes. All right, let's say we keep rotating that terminal side till we make it a 180. Now it hits the circle right there. What do you think the coordinate is for 180 degrees? Yeah.
Negative 1, 0.
Negative 1, 0. And lastly, we could have the terminal side rotated around 3/4 of the way. So now you'd be looking at an angle like that. These other ones would be here. And what do you think the coordinate is for 270 degrees? Yeah.
0, negative 1.
0, negative 1. So those are 4 angles that are pretty easy to find the coordinate for. They each have a 1 and a 0, or a negative 1. In general, we can't find coordinates easily for every angle. Okay, we can do angles that are multiples of 30 and 45 pretty easily. Technically, we can also do 15s, but we won't get into that for quite a while. All right, so we're going to try using this method of finding the location of a coordinate if we're dealing with angles that are 30s or 45s and multiples. Okay, so I'll show you how that works. So this is basically what I've told you already. So the idea of unit circle trig is that for certain angles, specifically multiples of 30 and 45, that's what I mean by multiple, by certain angles, we can draw them on the circle and so I'll write it like this. Draw them on the circle and locate the coordinate. How can I say it simply? Locate the coordinate where the terminal side hits the circle. Locate the coordinate where the terminal side intersects the circle. I'll say it like that. Once you have that coordinate, we can use the x and the y value from the coordinate to figure some things out. But the whole key is we need the full coordinate. We need the x value and we need the y value. And specifically, what those x and y values allow us to do is find the 6 trig functions of an angle. Okay, of what angle? Well, again, let's say that was your point. So this would be your angle. That point in red has an x and a y part to its coordinate. And this is the angle that I'm talking about. So if you knew the coordinate of that red dot, you would be able to find the 6 trig functions corresponding to the angle. What angle? The angle in green. So this might, I think this is the first time you've ever seen the trig functions in this class. So I'm going to write out what they are. I'll show you the abbreviations for them. And then I'll show you the formula. Like how do you calculate a trig function based on knowing a location? So, let's take a look. All right, seems like we're missing a page, but that's okay. I can fill that in. Definitions of the 6 trig functions on a unit circle. Okay, and here are the 6. The first one is sine. The second one is cosine. And the third one is tangent. Have we written these out yet? No. Okay, so we'll write these out. Their abbreviations I'll put below. Sine, we abbreviate SIN. Cosine is abbreviated COS. And tangent is abbreviated TAN. So let me go back to our diagram. This angle that I have in green right here, we don't know what it is. Okay? It's bigger than 90, but we don't know what it is. So generally, when we have an angle that we don't know in trig, we represent it with a Greek letter. I think we said that before. So now what you can do is you can take that angle and you can plug it into one of these functions. You can plug it into the sine, you can plug it into the cosine, or you can plug it into the tangent. And when I put it like that, it's basically what I'm representing here is this is an argument. It's the thing that you would plug into that function. Just like if you had, let's see, we studied logarithms, okay, earlier in the year. Log of 4. 4 is the argument. It's just the thing that I'm going to plug into the log formula. Theta is the angle that I would plug into the sine formula. Yeah, how do you figure out the sine based on knowing the coordinate? Well, the sine is equal to the y value. Cosine is the x value, and tangent is y over x. And again, if you don't remember what that is, I can write it here. X comma y represents where the terminal side hits the circle. Okay, you wrote that on the previous page. I'm just writing it again. So xy is the location where the terminal side hits the circle when you draw your angle. All right. The other three trig functions are cosecant, secant, and cotangent. Usually an abbreviation uses the first three letters. We went into a little problem with cosecant. We've already used the first three letters of that for cosine. So the way they abbreviate cosecant, cosecant, CSC. They just go by syllables. Then we can go back to the first three. That's secant. And that's the abbreviation for cotangent. And again, those are three other functions in trig that you can plug something into. Just like you can plug something into a square root function, plug something into a log function, we plug an angle into these functions. Now, what if we don't know the angle? Not a problem. We don't need to in this section. All you need to know is the coordinate of the angle. You don't actually have to know the angle itself. You need to know the xy coordinate. Now, the relationship, and the way I set them up, I purposely wanted sine across from cosecant, cosine from secant, tangent from cotangent. Because the connection between these is they are reciprocals. What does it mean if you have a reciprocal? What is that? Yeah?
Flip the numerator and denominator.
Yeah, it's when you take something and you flip it. So, if this is y, you could put it over 1. I'm going to erase the over 1, but you could put it over 1. If you flip y over 1, what do you get? Yeah?
1 over y.
1 over y. And that is the definition of the cosecant. It's the reciprocal of the sine. Since all of these are reciprocals, anybody have a guess what the secant would be? Yeah?
1 over x.
It is 1 over x. It's the reciprocal of the cosine. And how about cotangent? Yeah, Jake?
X over y.
X over y. So you can see all 6 of these formulas depend on knowing the location of the coordinate for an angle. So like you guys already know the coordinate for 0, 90, 180, and 270. Okay, we've got those 4. So we could do those. But I'll show you what happens when it's not 0, 90, 180, or 270. Okay, any questions on those definitions? All right, so let's try an example. Find the 6 trig functions of pi. Pi is an name. Maybe not the easiest to work with because we're just getting used to this system, but anybody remember what the units are if you don't see the little circle? Yep, I know.
Radians.
Radians. Okay, that's in radians. Now the whole goal is you have to be able to find the coordinate. If it's easier for you to figure out the coordinate with that in degrees, fine. Then change that to degrees and think about it that way. But if you know the coordinate for pi at the top of your head, then that's all we need. I'm guessing most people are probably going to want to change that. All right, so let's change pi to degrees. Anybody remember what pi radians is in degrees? Or if not, does anybody remember how we convert it? Yep. Yeah, it's 180. Multiply by 180 and you divide by pi. That's how you would convert it. And if you multiply by 180 and divide by pi, you'll get 180 degrees, which is something we know the coordinate for. Okay. Can somebody remind me? What is the coordinate for 180 degrees? Yep.
-1, 0.
-1, 0. Now, we have an x, we have a y. Fill in those x and y values into those 6 windows. So let's start with sine. What would the sine of pi equal? Yeah.
0.
0. Sine is my y value. My y value in this case is 0. Done. That's the sine. Matt, how about the cosine? What's the formula for cosine?
X.
X, and what's my x value here?
-1.
And that's it. -1. Okay, let's look at the tangent. Abigail, what's my formula for tangent? Y over x. So in this case, 0 divided by -1. I'm just going to put that over here for a second. And what do you get when you divide 0 by -1? Yep?
0.
You get 0. Now, we really don't have to think about, well, wait, what's the formula again for cosecant? No. Just take what you had before and flip it. So let's start with the sine. How could I make that a fraction? Because I want to flip it, but to flip it, I need it to be a fraction. So I could put, yeah.
0 over -1.
0 over what?
-1.
So we can't,
Oh, 0 over 1.
yeah, if we want to make something a fraction, we can't use a -1, but we can use just a positive one. All right, and Ethan, what do you get if you flip that?
1 over 0.
You get 1 over 0, and what happens when you try to divide by 0? Yeah.
Undefined.
Undefined, you can't divide by 0. Undefined. So you would literally type that in as the answer, undefined. Or you could type, undef, that's fine. All right, so now to get the secant, let's go back to the cosine and flip it. What would you get if you flip -1 over 1? Yeah. You would still get -1. There are two numbers you can flip and it doesn't change their value. You can flip the number 1 or you can flip the number -1. There's no change. Alright, so we already did 0 up above, so now we just have the same thing again, and we already know if you flip 0, undefined. Any questions about that? Now, another way you could see this problem that would be a little bit easier would be like this. We're not going to do it because we just did this problem. Find 6 trig functions of the angle represented by -1, 0. That's actually an easier problem because I'm giving you the coordinate right away. I'm not giving you an angle which then you have to figure out the coordinate from. I started you off with the x and the y values right away. So if they start you with a coordinate right away, you can just go right to the formulas. You don't even have to figure out the coordinate. Sometimes they do, sometimes they don't. If they do, great. If they don't, well, then you have to find the coordinate first, just like we did in this problem. Okay? Any question on that? All right, so that was that one. Okay, let's try this one. Find the 6 trig functions of 7 pi divided by 2. All right. What might it be a good idea to do with this one? And this is going to help us to find the coordinate. Yep.
Switch it to degrees.
Yep, I would change it to degrees. Now remember, you can multiply by 180 and divide by pi, but the way I think of it in my head, does anybody remember what pi divided by 2 is? Yep.
90 degrees.
90, because we just did pi, right? In the last problem, pi was 180. So this is 180 divided by 2. So this part circled is 90. What's 90 times 7? Oh, Casey? So remember, this part is 90, right?
Oh, yeah.
So 90 times 7. Yeah.
630.
630. Now, that's kind of a big angle to work with. I'm not sure where that would be on the circle, but we talked about last time, what can you subtract from an angle to make it smaller, but it won't mess up the answer. You could add or subtract it. In this case, we need to subtract it. We need it smaller. Yeah.
360.
Yeah, we can subtract 360. So let's take 630. Oops. Let's subtract 360 and see if we recognize that as something. 270. Okay. Now, I'm not going to put equals the coordinate because it doesn't really equal the coordinate. The coordinate is how you represent the angle. Okay. So what is the coordinate for 270 degrees?
0, -1.
0, -1. Now we can go through and do exactly the same thing we just did before. All right. So Zach, what is my sign going to be?
Zero.
What's the definition of sign?
Y.
Y. And in this case, my y is
-1.
-1. Yeah. All right. Tyler, how about my cosine?
Zero.
Yep. Cosine is defined to be the x coordinate, the x part of the coordinate. In this case, that's 0. And Bailey, how about my tangent?
-1/0.
Yeah, what you can do for tangent is just imagine putting a division line right there. Because you already have your y, you already have your x, just divide them. So it's -1/0. And Jake, if I simplify negative 1 over 0, what's that?
Undefined.
Undefined. You can't divide by 0. You do have to tell me it's undefined. So I know that you know dividing by 0 is undefined. Okay. Now we've got the 3 on the left. Sarah, what am I going to do with the 3 on the left to get the 3 on the right? Yeah, we're just going to take the reciprocal. We're going to flip each one of them. All right. So Matt, what do I get when I flip negative 1?
You get 1 over negative 1.
Which is?
Negative 1.
It's just negative 1. Stays the same. Abigail, what do I get when I flip 0? Which is? Undefined. And Jack, when I flip undefined, I get?
Undefined. 0 over negative 1.
And what is 0 divided by negative 1?
0.
0, yes. And those are the 6 trig functions for 7 pi over 2, or 270 degrees. Any question on that one? Again, it would have been easier if they had just given me the coordinate right away. They didn't, so I had to do a little bit of work to figure that coordinate out. Okay, negative 90. I don't like that angle because it's negative. How can I fix it? Jake?
Subtract 360.
Okay. So negative 90 minus 360. Now I have negative 450.
Oh.
Oh.
360.
So we're going to add 360. So that's 270. Wait a minute, we just did that problem. This is the same problem. So I'm just going to write C, example, was it example 5? Yep. So there's a lot of different ways I can ask a question, and it might look different. Like find the 6 trig functions of negative 90. Find the 6 trig functions of 7 pi over 2. Same question. Questions why that would be the same answers. All right. Okay, so that's the end of 6.2 part 1. So we'll start to take a look at 6.2 part 2. And see, I didn't plan on finishing it, but we finished it out really fast. So let's see. All right, so second part of 6.2, basically we're going to extend what we learned in part 1, except now we're going to look at what if we had angles that aren't just 0, 90, 180, and 270. Those are easy to find the coordinates of. We're going to look at finding the trig functions for 30s and 45s and multiples. Multiples are super easy if you know how to do it for just the regular 30s and 45s. Okay, so pi over 6, that represents 30 degrees. Pi over 3 is 60. Pi over 4 is 45 degrees. So we'll start with those 3. And then we'll do multiples of them, like 120. That's a multiple of 30. And we're not going to work with trig identities. That's something that they put at the end of the section, but we're going to spend other sections on it, so not going to do that. Okay, so let's start with a 45-degree angle. So, just like I've done for different angles, I got 0 degrees here, 90 here. 45 degrees would basically be a ray with a slope of 1. It would be halfway between 0 and 90. And here's the coordinate where the terminal point hits the circle. That's what I need to find. So remember what a coordinate means. X measures horizontal movement, y measures vertical movement. That line that I just drew in would that represent an x value or a y value? Tyler?
Well, you know, the x value, right?
That vertical line, that one that I just put in?
Yeah.
So x is up and down?
Oh, no, I thought you meant like that one and that one. Then yeah, y value.
Yeah, this would represent y. It's a height. So this would represent the y. This is the x. So starting from the origin, my goal was basically to figure out how far right and then how far up do I have to go. If you can tell me those two things, that's the coordinate for 45 degrees. How far right and how far up. Now, this is a 90. This angle is a 45-degree angle because that's the angle that I tilted the hypotenuse at because I wanted it to be 45. What's this angle at the top going to be? Okay.
45.
That's also a 45. Because all the angles in a triangle have to add up to what? Yeah.
180.
They'll have to add up to 180. So if that's a 45, because that's how we set the hypotenuse, and that's a 90, then the other one has to be a 45 to add up to 180. Now, that's a right triangle, but it has two angles that are the same. So what does that mean about it? That makes it something else. Compared to a triangle that had three different angles. This one has two angles the same. What does that mean? Yeah. It's isosceles. Yeah, that's an isosceles right triangle. So isosceles not only means you have two angles that are the same, you also have, yeah.
Two sides.
Yeah, two sides that are the same. Which two sides are going to end up being the same in that triangle? Yeah.
The X and the Y.
Yeah, the x and the y really are the same. So technically, we don't need different letters. We could call them both the same letter. Because whatever the base is, that's the height. So I drew the same triangle right here. Just a little bit bigger so I have more space to work. And I'm going to call both of these sides x. There's no reason to use two different letters if they're really going to end up being the same thing. You could call them both y. Okay, but whatever you call them, use the same letter for both. Now, what is this side in my triangle? Yep. It's the hypotenuse. What is that side in my circle? Yeah. It's the radius. And remember, we're dealing with a unit circle, which means the radius is automatically what number? Yeah?
1.
1. Okay, the radius here is 1, which means I know the length of the hypotenuse. It's 1. Now my goal is to solve for x. Does anybody remember the name of a theorem from geometry? That if you know a side in a right triangle, you can find the other ones. Yeah?
Pythagorean theorem.
Yeah, we're going to do the Pythagorean theorem. Can you tell me what the Pythagorean theorem, how it's generally written? And then I want to apply it to those letters.
A squared plus B squared equals C squared.
Okay, can you explain what those letters mean?
A squared and B squared are the two sides, and C squared is hypotenuse.
So A and B are the two short sides, those are the legs, and C is the hypotenuse. How long are both my legs in this model? Yeah,
X.
x. So in our case, one of the legs is x, the other leg is x, and Jack, what's C going to be? 1. So let's fill in these letters into Pythagorean theorem and solve for x. This wouldn't work if these two letters were different. That would be a problem. then we'd have two variables. Right now, we really only have one variable, just an x. X squared plus x squared. And I'm just going to do that out. 1 squared is 1. How about, Casey, what's x squared plus x squared? How much?
2x squared.
Yes, good. 2x squared. All right. Ashley, what would be my next step to get x squared by itself?
Divide by 2.
Yep, and divide by 2. Divide by 2. So x squared equals a half. And how do I get rid of having an exponent of 2? I don't want x squared. I want just x. Yeah.
Take the square root of both sides.
Take the square root of both sides. And when you have to square root a fraction, you do the top and the bottom separate. Top, bottom. That cancels. So we get 1 over, the square root of 1 I can do is 1. I can't do the square root of 2, but we're not allowed to leave a square root in the bottom of a fraction. So anybody remember, what do you multiply the top and the bottom by? To fix having a square root in the bottom. Yeah.
Square root of 2 over square root of 2.
Yep, you multiply, it's just a trick from algebra. Multiply the top and the bottom by the square root. It's not going to get rid of it, but it'll move it to the top instead of being in the bottom. And now multiply straight across. Ethan, what's 1 times the square root of 2?
1 square root of 2.
Just 1 square root of 2. And what's the square root of 2 times the square root of 2? That's like the square root of 2 squared. Yeah. How much?
2.
2. Yeah. That's the square root of 4, or just 2. Now, we know what x is. And x was the length of each side in the triangle. It's square root of 2 over 2. So this side is square root 2 over 2 from here to here. And this side from here to here is square root 2 over 2. So, based on that, anyone think they can tell me the coordinate for 45 degrees? Yeah.
Would be square root of 2 over 2 and square root of 2 over 2.
Yeah. Square root of 2 over 2, comma, square root of 2 over 2. That's the coordinate for 45 degrees. So the x and the y are the same. Now, when we do a 45-degree angle in a different quadrant, so you have this one. This is 135. That's the multiple of 45 in quadrant 2. That triangle in black is just a reflection of the triangle I had in quadrant 1. When you reflect a shape, does it change the length of the sides? No. So both of these are still square root 2 over 2, square root 2 over 2. But what's going to be different about the coordinate for 135? Yeah.
The x is going to be negative.
The x value is going to be negative because 135 is in quadrant 2. If you did the 45-degree angle in quadrant 3, it would be right here. Anyone think they can tell me what the halfway mark would be in quadrant 3? Yep.
Would it be the square root of 2 over 2? No, hold up. The negative square root of 2 over 2, comma negative square root of 2 over 2.
Yeah, they'd both be negative because you're in the third quadrant. And how about the angle? That coordinate would represent an angle of, I mean, it's more than 180, but it's less than 270. It's in between. Yep.
225.
That's a 225. And you could also do a 45-degree angle over here. That would be 315. And the coordinate for that would be root 2 over 2, comma, negative root 2 over 2. So the point is, you don't have to memorize 4 different coordinates. All you have to do is remember, any angle that's a multiple of 45 degrees is going to have a root 2 over 2 and a root 2 over 2. You just have to decide, are they both positive? Are they both negative? Or do you need one of each? And we never have to go back through and figure out that root 2 over 2 again. We just want to remember that, put it on a reference sheet, so we can use it in the future. All right, any question on that? Okay, so those are the 45s. It starts to look a little confusing if you draw everything out. That's why I usually just stick to drawing one of them. And you can just imagine flipping it. All right, so let's try this problem. Find the 6 trig functions of 45 degrees. Okay. Anytime that I want to do unit circle trig, what is it that I must have? And without this, I can't use any of those 6 formulas. Sarah?
The coordinate.
You have to have the coordinate. You either have to calculate it, which is kind of a pain, or you just have to memorize what it is, write it on a reference sheet, something like that. All right. So 45 degrees. Can someone remind me what is the coordinate for a 45-degree angle? More specifically, it's where the terminal side hits the circle. Yeah?
The square root of 2 over 2, comma square root of 2 over 2.
Comma square root 2 over 2. That's my x, and that's my y. And now we can do all the trig functions just like we did in the first part. Okay, let's start with sine. Matt, what's the definition of sine again? It's which letter?
Y.
Y. And what's my y in this case?
Square root of 2 over 2.
Yep. If you mix them up, you get lucky this time because they're the same. But really, we should know which one is which. Okay, cosine. Abigail, what's the formula for that? Yeah, x. And what's my x value in this case? Good. Square root of 2 over 2. Now, tangent is when you divide the y by the x. Well, the y and the x are the same. So what am I going to get for the tangent of a 45-degree angle? Yep. 1. And now, Eli, once I have the 3 on the left, what do I do to get the 3 on the right?
Flip them.
Flip them. I'm gonna do cotangent first, just because I think that one's quick. What do you get when you flip 1? Yep. 1. It stays the same. And the nice thing is, when I flip the sine, well, it's the same as the cosine. So once I figure one of these out, then I'm done. All right, so let's flip the sine. You get 2 over the square root of 2. Is that okay for a final answer? No, what's wrong with it, Zach? Yeah, we got the square root at the bottom. So what do I multiply by to fix having the square root in the bottom? Yeah.
The square root of 2 over the square root of 2.
The square root of 2 over the square root of 2. That's going to give me 2 times the square root of 2 in the top. And Tyler, what does that give me in the bottom?
2.
2. And now look what just happened. 2 times something divided by 2. Well, if you're going to take something and double it and then divide it by 2, that cancels out. All you're left with is the square root of 2. And that'll probably be one you remember after a while. Whenever you flip root 2 over 2, you get root 2. Okay, so we won't have to go through that every time. How about the secant? What's that going to be? Jake?
Square root of 2.
It's the same as the one above it. Since sine and cosine were the same, secant and cosecant are the same. Okay. Any questions on finding the 6 trig functions of a 45-degree angle? All right. So next, we're going to look at the 30s and the 60s. Let's start with the 30. Okay, don't even draw the 60-degree if you don't want to right now. So here's the 30. That's a 90. This angle, like this. This angle right here is my 30. And what would this angle at the top be? Yeah, you like?
60?
Yeah, this one would have to be my 60. Again, don't even draw the 60-degree triangle right now. Just draw the one in red. Now, is that an isosceles triangle? Jake? No, so we can't do the same trick of the Pythagorean theorem this time. Because the problem is you would have one side that is x, you'd have another side that's y, and they are different, so you need to use different variables. Well, if you plug that in Pythagorean theorem, you'd have x squared plus y squared. That's 2 variables, that's not going to work. So let's take the same thing, draw it off to the side, and I'll give you a hint. Let's start with the hypotenuse. How long is the hypotenuse of this triangle? Well, remember the hypotenuse is also it's the hypotenuse of the triangle, but what is it in the circle? Matt?
1.
Yeah, it's the radius of the circle, and that makes it 1. So we know that's 1. Unfortunately, that's not what I need. I need the base and I need the height, and that's my x and my y. Let's just start out with which one is bigger. Do you think the x value is going to be bigger when we do the coordinate of 30? Or do you think the y value is going to be bigger? Okay? The x is going to be bigger. Bigger angle is across from a bigger side. Smaller angle is always across from a smaller side. So the x is bigger. Okay. And here is my hint. I'm going to go like that. And then I'm going to go like that. Okay. What could I do with those 2 things? Matt?
to 1.
Okay, so I want to make them into, what shape am I going to get when I do that? Yeah,
Triangle.
yeah, I'm going to get another triangle. Okay, I'm just going to combine them. So double here, good enough. All right, so I combined them. Now, I know I have a triangle, but I want to even be a little bit more specific. What kind of triangle is that big triangle now? Anybody notice it? Yeah?
Isosceles?
Um,
Or equilateral?
It's equilateral. This is 60, this is 60, this is 60. All the angles being the same means all the sides that are the same. So we know that side is 1, this bottom side is 1, but more importantly, this side is 1. Now, what do we know about the side in red compared to the side in green? How does the red side and the green side compare? Yeah,
They're the same.
they're the same because they're mirror images of each other. So they are congruent. So if those two sides are congruent and they have a total length of 1, how long does each one of them have to be? How long does each one of them have to be? Yeah, a half, right? Each one of them has to be 1/2 because they have to add up to 1 and they're the same. So a half and a half. We've now figured out one of the sides. Now we can use Pythagorean theorem because we won't have two variables. We know the y value is 1/2. I don't need this bottom triangle anymore. You can keep it, but it's just less busy if I move this stuff away. All right, so this side is a half, and the bottom side represents which part of my coordinate? My x or my y? Okay, x, so let's call that x. And now let's set up Pythagorean theorem to solve for x. Again, no problem anymore because now you have two sides that you know and only one that you don't. We just had to use a little trick to figure out this other side was a half. Okay? But now we know it, so we don't have to do that again. All right, so how about, Ashley, could you plug in the Pythagorean theorem using the values in that triangle?
It would be x squared plus 1/2 x, or 1/2 x squared
Half squared, yep,
equals 1.
perfect. And you can put squared, we're gonna square it, it's just gonna come right back to 1 anyway. So x squared plus, what's 1/2 squared? That's half of a half. Yep,
4.
that's a fourth. Okay, Jack, what would be my next step to get x squared by itself?
Subtract the 1/4.
Yep, subtract the 1/4. And what do you get if you do 1 minus 1/4? 3/4. And my last step, we had to do this before to get rid of the exponent of 2, is to do what? Tyler?
Square root.
Yep, I'm going to take the square root and do it just like you did before. Because it's a fraction, you need to do the top and the bottom. And we get x equals. Eli, does the square root of 3 have a nice answer?
No.
No, so we're just going to leave that. How about the square root of 4?
2.
2. There's the length of the bottom side, which is the x value of my coordinate. Square root 3/2. That is always the coordinate for 30 degrees, and that never changes. Now, for 60 degrees, you might think, oh, great, you gotta go through the whole thing again. Not really. Look at this triangle in blue and compare it to the one in red. What's the difference between the blue one and the red one? Tyler?
It's like they're flopped, like the X and Y.
Yeah, it's the same triangle. The only difference is if you took the red one and then just kind of like stood it upright on its, so it was on the short side, and then like flipped it, the red and the blue are exactly the same triangle. There's no difference. So it's exactly what Tyler said with the coordinates. Now, the short side is on the bottom, and the short side is always the 1/2. Okay, we agreed right at the beginning that x was bigger than y when we did the 30. Y is shorter. The short side is always the 1/2, and the long side is always the √3/2. And that makes sense, because if you did these as numbers, 1/2 is 0.5. √3/2 is about 0.87. It's bigger. √3/2 is a bigger number than 1/2, and it is always the bigger side. 1/2 is the short side. So that's the only extra thing you have to think about when you do the 30s and the 60s. They always involve those two fractions, 1/2 and √3/2. It's just we have to label the long side and the short side correctly. So let's say I had this triangle right here. That's a mirror image of the red one. Anyone have a guess what angle that would be? Jeff?
150.
That's a 150. Oops. That's a 150. Now, when we write the coordinate for it, this side is the long side. So that's √3/2. That's the short side, so it's 1/2. But what's going to happen to the x value? Because we're in quadrant 2. Yep,
It's gonna be negative.
it's going to be a negative. So this is negative √3/2, comma, 1/2. Now, I'm not going to draw all the 30s and 60s because there's 2 I could put in every quadrant. I did the 2 in the first quadrant, but you could have 2 here, 2 here, 2 here, and 2 here. If you draw all 8 of them, then it looks, it starts to look real confusing. Okay, but you don't need all 8. All you have to remember is 2 numbers, √3/2 and 1/2. Short side, 1/2. Long side, √3/2. Let's try this one. Find the 6 trig functions of 30 degrees. Okay, what do I need here first that they did not give me? Yeah, I need the coordinate. Now I gotta be careful. The 45 is easier because they're both √2/2. This one uses √3/2 and 1/2. I just have to get them in the right order. If you forget, make a sketch. Doesn't have to be perfect, it just has to be reasonable. Put 30, and I'll write about there. Draw your triangle. If you draw it reasonable, it's pretty easy to see which side is the long side and which side is the short side. The short side is always what number? Yep, 1/2. And the long side is always, yep, Jake,
3 squared over 2.
say it again.
Oh, 3 square root of 3 over 2.
Square root of 3/2. Now I can easily see the coordinate for 30 degrees. X is √3/2, y is 1/2. Just by making a quick sketch. 3/2, comma, 1/2. All right. So Abigail, what's the definition of sine? Y. And my y in this case, Jack, is 1/2. Good. Casey, definition of cosine.
Square root 3 over 2.
Yep, it's the x value, which in this case, root 3 over 2. And Eli, my tangent?
1 over 2 over square root of 3 over 2.
All right, sounds a little complicated. 1/2 over root 3 over 2. What do we do, Eli, when we have to divide a fraction by another fraction?
Do you like multiply by the inverse or
Multiply by the,
inverse or the bottom?
yeah, we do something to the bottom. Anyone remember the word for that? Multiply by the, yep,
Reciprocal.
reciprocal. Keep the top the same. Multiply the bottom by the reciprocal. And Zach, when I do that, what cancels out there?
The 2.
The 2's, because whenever you're multiplying, you have the same thing in the top and the bottom, just like when we did the units with angular velocity. Same thing in the top and the bottom, cancels out. And you have this. 1 in the top, square root of 3 in the bottom. Is it okay to leave it like that? No. What do I have to multiply by to fix it? Tyler?
The square root of 3 on top
And bottom. And when I do that, 1 times the square root of 3 is the square root of 3. And what's the square root of 3 times the square root of 3? 3. There we go. Now, don't forget about this. We'll come back to that. That might come in handy. It's still good that we did that. All right. Now, how do we get the 3 on the right based on using the 3 on the left? Okay.
Can you repeat what you said?
How are we going to get the 3 on the right?
The reciprocal on the left.
Yeah, just take the reciprocal of the one on the left. So Sarah, what's my cosecant going to be?
2 over 1.
2 over 1. We'll just do 2. Anyone think they can give me my secant fully cleaned up? Because think about what's going to happen when you flip it. And then you got to fix that. Yep.
2 times the square root of 3 over 3.
Perfect. That's the secant, all cleaned up with the root not in the bottom. Now, let's look at the cotangent. The box in green and the thing circled in blue for tangent are the same thing. Since they're the same, I could flip either one of them. Which one would be better to flip? Yeah.
The one in green.
The one in green, how come?
Because you won't have a square root on the bottom.
Right, if we flip the one in green, the square root goes to the top, and we're done. If you flip the blue one, the square root's going to go back to the bottom. You're going to have to fix the whole thing all over again, but you'll end up with the same thing. Okay, any question on that? Let's see. Let's find just these 3 trig functions of 135. Not all 6, just these 3. All right, so what's the first thing that I need to find the trig functions of any angle? I have to make sure that I know. Eli?
Coordinate?
Gotta have the coordinate. So let's think about 135. Is that going to be a multiple of 30? Or is that a multiple of 45? Yeah,
45.
that's a multiple of 45. I like those better because then both the x and the y are the same, except for the positive or negative on the coordinate. Since it's a multiple of 45, that means it's exactly halfway between the 90 and the 135. So here's your x, here's your y. How long is each side when you're dealing with a 45-degree triangle? A 45-45 90 triangle. And don't worry about the coordinate, like positive and negative, yet. Just the length of each side, so?
Square root 2 over 2.
Yep, they're both square root 2 over 2. Now you're doing 135. So what's going to be the coordinate for 135? Cut it?
Negative square root over 2 over 2, and then positive square root 2 over 2.
Positive square root 2 over 2. Perfect. Now they just want the sine, the cosine, and the tangent. How about Bailey? What's my sine?
Square root of 2 over 2.
Yep, it's my y. Matt, what's my cosine?
Negative square root of 2 over 2.
Good, that's my x. And Abigail, what would be my tangent of 135 degrees?
Negative 2, negative square root of 2 over 2 over 2.
What's the formula again for tangent? Yeah. So it's y over x. But what do you get when you divide the y by the x here? Negative 1. We're dividing two numbers that are opposites. And that gives us negative 1. Okay, we don't have to do the other three because they didn't ask for them this time. Any questions on those? All right. How many of these do I have? I think. Okay. This one, let's just do the sine and the cosine. So now we're only going to do two of them. 7 pi over 6. Ethan, first thing I have to do.
Get the coordinates.
Get the coordinate. Well, how can we make this easier to work with to get the coordinate?
Make it to degree.
Change it to degrees. I'll tell you when you change it to degrees, if you follow the steps I showed you, you will get 210 degrees. So now, let's think about where that is. Is 210 a multiple of 45 or 30? Yeah.
Wouldn't be 30.
That's a multiple of 30, which means it's not right in the middle. It's closer to one of the axes. In this case, 210 is a lot closer to 180 than it is 270. So let's put it right here. Make our triangle. Short side. How long is a short side in a 30, 60, 90? Okay.
Negative 1/2.
Yeah, it's going to be, we'll worry about the negative in a minute, but that side is going to be 1/2. Yep. And how about the long side? Okay.
Square root of 3 over 2.
Square root of 3 over 2. And what Tyler started to say, both the x and the y in this case are going to be what kind of number? Yeah, they're both going to be negative. So negative 3 over 2, comma, negative 1/2. Okay, let's do the sine. Sarah, what's my sine?
Negative 1/2.
Good. So the sine of 7 pi over 6 is negative 1/2. What's the cosine of 7 pi over 6? Yeah,
Negative square root of 3 over 2.
perfect. Okay, any questions on those two? All right, we'll do the last thing, which is super easy. If I ask you about a trig function that's not a multiple of 30 or 45, you're not going to be able to do it with what I taught you about the circle. You're going to have to use a calculator. So this part is just, how do you type it in on the calculator? So find the 6 trig functions of 42 degrees. First step, you'd have to ask yourself, is 42 a multiple of 30 or 45? Is it either one? Eli?
It's neither.
No, it's not either one of them. So how do we type them in? Very easy. First thing is, look at your angle. What units are on this angle? Yep,
Degrees.
degrees. My calculator is not in degrees. I need to press mode, and then I can change it to the degree setting. If you don't do that, it will come out wrong. And now we type it in. Sine 42, cosine 42, tangent 42. That's simple. There is no way to do this one with coordinates on the circle. Now, if you look at the calculator, is there a button on it that says CSC, SEC, or COT? Yeah?
Don't you just press the second key and then the sign button?
If you press the second and the sign button, that's inverse trig. We're going to talk about that later after Christmas. So, how did we find the cosecant if we knew the sign? What did we do? Yeah. It's just the reciprocal. Do it exactly the same way. 1 divided by the sine of 42. There's your cosecant. 1 divided by the cosine of 42. There's your secant. 1 divided by the tangent of 42. There's your cotangent. That's how you do the ones that you have to flip. Cosecant, secant, cotangent. Any questions on that? All right, so let me give you guys the homework. I think we've only got 5 minutes to finish up in this section, so we'll easily finish this tomorrow. Yeah, that's it. And then we skip the stuff on identities. Okay, so on page 335. Let me adjust this a little bit. 13 to 16. That should be fine. 21 to 24, that's fine. 29 to 32, you don't need a calculator. 37 and 39, that's good. 45. All right, we'll do these tomorrow. And I want to just add one simple one that we did at the beginning. Find the 6 trig functions of 90 degrees. That's from the first part. All the black questions are from the second part. I think I want to give you one from the first part. Okay, so that's homework for tonight, and then we'll take a look at that